I came across this very interesting debate growing among data scientists: Pytorch or TensorFlow. There are tons of blogs written over the internet for the same. Some say TensorFlow is the best, while others prefer the counterpart, Pytorch. These days, even companies are mentioning frameworks like Pytorch or TensorFlow over the job description. Generally, it doesn't even matter which framework you use. If you know the basics, molding yourself towards any framework becomes super easy. That's exactly what I'm going to show you guys through this series of videos we are going to create on Pytorch. For today, the agenda is to break down the very basic storage unit in Pytorch named as tensors. What are tensors? Let's dive in. Imagine a vector as a single row or column of numbers. That's a 1D array, or in other words, a one-dimensional tensor. Next, we have matrices. Think of these as a table of numbers, like a spreadsheet. You have rows and columns, making it a 2D array. So, a matrix is a two-dimensional tensor. Simple, right? So, what's a tensor? Well, tensors are like the ultimate storage solution for numbers. They can hold all these arrays in multiple dimensions, whether it's a vector, a matrix, or higher dimensions. A tensor's got you covered. So without wasting any time, let me just go over to my local Jupyter notebook and get started with the exploration of tensors. So in order to begin with the implementation, the first step would be to import the libraries. But if you haven't worked with it before, there is a possibility of it throwing an error. So we will go ahead and install Pytorch using the pip space install space torch command, right? So now, as you can see, our requirement is satisfied. Now we can go ahead and import the library using import space torch. So now our first topic would be to create a tensor. Let's see how that is done. So first, let's try and create an empty tensor. So an empty tensor is basically a command using torch.empty, and all we have to do is pass the size of our tensor as a parameter. So let's say we want a tensor of size 3, and we'll print it. So this is the output. It's created an empty tensor. It's basically a tensor with uninitialized data, right? We can go ahead and check the data type of this tensor using t1.dtype, and as you can see, the default data type value is float 32. But in case we need an empty tensor of data type integer, so it is very easy. We can do it using torch.empty, and when we pass the size of the tensor along with that, we can explicitly define the data type using dtype equal to torch.say int. We'll run it, and you can see there are no decimal values, they're just integers, and you can see the data type is torch.int32. Basically, it's an integer data type, right? Now, let's say we want to initialize a tensor having random float values. So, how do you think this can be achieved? Well, it's very simple. All we have to do is we'll create another variable to store our new tensor, and all we have to do is torch.rand, right? And we can pass the size of our tensor again, and let's go for a 3-dimensional tensor using 5, 4, and 3. When we print it, this is the output. We have 5 elements having 4 rows each, and each of these elements also have 3 columns. It's like 4 rows, 3 columns, and 5 elements. So this is our 3-dimensional tensor created using random. And as you can see, these are all float values, right? We can also check the data type using t3.dtype, and you can see it's float. Now, what if we want a tensor having random integer values, right? So how can we do that? Now, if you try to explicitly define dtype over here as a parameter, it will throw an error. Let's give it a try. we have this as our size. Let's put it in brackets and then explicitly define the data type using dtype equal to torch dot int, right? So there we got an error. So in order to get an integer tensor having random values, we have to use a different function provided by Pytorch, which is torch dot randit. Now this function takes the lower value, we can say 0, the upper value, we can say the limit is 20, and the other parameter, which is very important, is the size. So let's say the size is 5,4. We'll print it and see how it looks. Okay. So we have 5 rows, 4 columns, and all these values are in the range of 0 to 20. Correct? So this is how we can create a random tensor having integer values. Now, what if we want a tensor filled with zeros? That is a tensor initialized only with 0 values. Correct? So that is also very easy. All we have to do is torch dot zeros, and again all we have to do is pass the size of our tensor. We can say 2,3, and we'll print it, and this is what it looks like. Now similarly, we can also create a tensor which is filled with ones, that is a tensor initialized with 1 values. So all we have to do is torch dot ones, and let's make it 3-dimensional using 2, 3, 4. So here we have 2 elements, each containing 3 rows and 4 columns. And all these values are 1. Now, as you can see, this is a float value. Let's check the data type. So it's float. What if we wanted an integer? All we have to do is pass the d type equal to torch dot int. So now it's converted to an integer data type. Right? Another important function of Pytorch is size. So if we want to check the size of any tensor, all we have to do is call the size method, and it will return the number of elements, rows, and columns respectively. There's another important method called dim, which tells us the dimension of the tensors. So all we have to do is pass this, and as you can see, this is a 3-dimensional tensor and it returns the number 3 over here. Now let's consider a scenario where we have a Numpy array that we want to convert to a tensor, correct? So let's go ahead and create a Numpy array using the library Numpy. We'll go ahead and create an array of, say, ones. Similarly, we have to pass the size in this as well. So this is our Numpy array containing 1 values. So if we want to convert this array into a tensor, all we have to do is call torch dot tensor and pass the array, and this is now a tensor. This is now converted to a tensor. So this method called dot tensor, torch dot tensor, can convert any array list to tensor data type. Moving on to the next topic, which is in place operator. Let me just write it down for you. Now, in place operator is basically, these are the operators that perform operations that change the context of a given tensor without making a copy. Right? So in place operators are basically postfixed with an underscore. Let's see how it's done. Now say you have a tensor T8 having torch dot ones as the initialized tensor. Let's give it size 2,3 and data type as torch.int. This is our first tensor, and let's create another tensor T9 in the similar manner. Correct. Now, if we want to perform addition on these two tensors, all we have to do is create another tensor T10 and say torch dot add T8 comma T9. Let's print T10. So as you can see, these two tensors got added and the result got stored in the variable T10. But what if we wanted the result to be stored in, say, T9 itself? So all we had to do is say T9.add underscore and T8. So what this is going to do is it's going to change the variable T9. It is performing in place operation. You can perform these operations for subtraction, multiplication and division as well. Let's take a look how that can be done. Say T9.sub and pass T8. So now it's like 2 minus 1. All the values got subtracted. Correct? Similarly, division and multiplication operations can be performed. I hope this is clear. Moving on to the next topic, which is reshaping the tensors. Correct. Now say we have a tensor of shape 2, 3. Okay, let's go ahead and create a tensor, or we can consider a tensor created somewhere over here. This is 2, 3 or T7. Correct. We'll consider T7. So say we have this tensor having size 2, 3, and we realize that the actual size we wanted was 3, 2. So we do not need to create another tensor, but instead we can just reshape this tensor itself using T7.reshape and then pass 3, 2. So easy, right? All we had to do is call the reshape method on the tensor that we want to reshape and pass the desired size as argument. So let's move on to the next topic, which is again very important, which is called Tensor Broadcasting. So Tensor Broadcasting is basically a technique that allows us to perform element-wise operations between two or more tensors having different shapes, but the shapes need to be compatible at the same time. Now, what is compatibility? Don't worry, we'll go into it in detail. So say we have two tensors, let's consider T7 and another tensor T6. So as you can see, these two tensors vary in shapes and dimensions. If you want to perform any operations on these two tensors, say we want to perform addition, let's try it out. T7 and T6, right? So here's the error. Since these dimensions do not match. Now this is where tensor broadcasting comes into picture, right? So what are the conditions of the tensors having compatible shapes? Let's check them out. 1, it has to be equal shapes, which is very obvious because if these two had equal shape, there wouldn't be any error. And then next, important point is one of the dimensions has to be 1. Now this case is applicable when shapes do not match, right? Now we'll go ahead and look at some examples. We'll create 2 tensors, empty tensors having shapes say 5, 4, 3, 2, or let's say 1. And another tensor having shape 1, 3, 5. So now if we perform addition on these 2 tensors, and let's store the result in Z, torch.add, and let's pass x, y. There we don't have any errors so far, and it has produced the results. Let's check the size of the resultant tensor. So now as you can see, it's become 5, 4, 3, 5. So what happened was there is 1 over here and 5 over here, right? So this will get broadcasted easily. Next we move on to 3 and 3, which is equal. Again, we have no problem. We broadcast further. Having 4 and 1. Again, 1, because there is 1 over here, we can easily broadcast and move further. 5, and this is basically like this, having no dimension over here. So there is no issue in performing any element-wise operations for cases like this. But say in case of 1, we had 4 over here. Now there's an error. So whenever we have different shapes, one of the tensors needs to have 1 and vice versa. So this is all about tensor broadcasting. Simple enough, right? Now we'll move on to vector multiplication. So whenever we want to multiply 2 vectors or 2 tensors, we use methods like matmul or mul. So let's consider 2 tensors. Tensor A, which is torch.tensor, and we'll pass a list of values like 10, 5, 6, right? And another tensor B, and we'll pass values like okay. And now let's go ahead and multiply these 2 tensors using torch.mul. We'll pass. Now what's the error over here? So basically this is our 1 into 4, which is having 1 row and 4 columns, and this is having 3 rows and 1 column. So this is why it's giving an error. We have to add another row so that the columns of the first matrix and the rows of the second matrix need to match to perform the vector multiplication, right? This is the basic standard rule. So we'll add another row, and let's see what our result looks like. So this is pretty much about vector multiplication. We'll jump into the next topic, which is transpose. So transpose is important for scenarios where we want to swap 2 dimensions, right? So let's see how it is done. We'll create another tensor using randint function, and we'll pass 0 to say 20, and we'll give the size 4, 5. Now I hope you understand why I gave 4, 5 as the size, because there are 20 elements, right? So our size needs to add up. So if we want to transpose this tensor, all we have to do is we'll store it in Y, and we'll call torch.transpose, and we'll pass the tensor. And the parameters that transpose method takes is dimension 1 and dimension 2. So now as you can see, we have 4, 5, right? First, let's go ahead and check the dimension of x. It's 4, 5. Now if we go ahead and give 0, 1 as our 0th dimension is 4 and first dimension is 5, and if we transpose and print the size, so as you can see, our dimensions have been swapped, they have been interchanged. This is what y will look like. So simple enough, right? Let's go ahead and perform indexing and slicing. Now we'll consider this tensor itself, tensor y, having these elements. Now say I want to extract the first element over here. So what should be my syntax? Y 0 0, and it's returning this element but in a bracket and telling us that it's a tensor. But if I want just the value, all I have to do is call this dot item method and it will return the value itself. We'll create another tensor, let's say T13, and we'll say torch dot randint, or let's just call rand, and we'll create a 3-dimensional. Okay, so it's a pretty big tensor, right? And it looks very confusing. So if we want to access, say, the last element over here, so how will that be done? Since this is a 3-dimensional tensor, we have to first access this is our first element, this is our second element, this is our third, fourth and fifth, right? And we know indexing starts from 0, so let's access the fourth one, and you can see we have access to the entire fourth element. Now we want to access the first, second, third, fourth row and last column. So we'll go ahead and access the fourth row. Third. Starts from 0, right? And then we go ahead and access the last one. -1 is basically reverse indexing. So this is how you can index any element from any matrix or any tensor, correct? Let's see how we would access these two complete elements, right? So this is our first element, this is our second element, this is our third element. So let's go ahead and access the second and third element of T13 tensor. So we start from 1 and we want the second as well, and you know the stop value is never counted. So we give 3 as a stop value and voila. This is our first and this is our second element, as you can see here. Exactly how we wanted it. Now let's go ahead and look at the last topic, which is reverse indexing. So in order to perform reverse indexing, usually what we have learned till now is giving -1 as the step value, right? Normally we would do this, colon and -1. We can reduce the space here, space is not required. But this is not allowed in tensors. It's giving the error step must be greater than 0. So what do we do here? Well, no worries, because Pytorch has its own method called flip. So in order to reverse any tensor, all we have to do is pass torch.flip, pass the tensor we want to flip, and we need to specify the dimension as well. Now say I want to flip it on dimension 0 and 1. Let's consider y. Now, if we want to reverse this tensor y, which is having these elements, let's see how that can be done, right? So all we have to do is call torch.flip, pass the tensor that we want to reverse, and then give the axis, that is 0 and 1. So after we print, this is what our tensor will look like after the reverse indexing using flip method is performed. So this is pretty much it. Now you know what tensors are as well as their implementation in Pytorch. I hope this video was helpful to all of you guys out there. If you have liked it, hit the thumbs up button. Also enable both subscribe button and the bell icon to receive more updates like this. Thank you.